Hello, friends. Now we're going to talk about using double integrals to find average values for a function. So you probably did some average value in Calc 1, and that would be the integral of the function, and we have it divided by the length of the interval. Well, here we aren't dealing with a number line and we're breaking it up into some, A to B value. We have an area. So in this case, we're going to take that double integral and divide it by the area. So a visualization that your text gives regarding this would be to think about we have some tank, right? Some tank with a base area. In this case, it's a right circular cylinder, but it's filled with water. And that water, if the tank was still, would be at a flat height. But in this case, the tank may be moving, and so the water is sloshing around. And we just want to find that average value for that volume shape, or essentially an average height. That's what we're doing with these average value problems. Our definition here is that the average value of a function over some region R is 1 over that area, your base area, and then the double integral across the region with respect to your function f. One other example we could think about where we might need to find an average value is if we had some thin plate which was covering R, and maybe we wanted to find the average temperature across that plate. So maybe there was some source of heat on the region, right? And obviously it's going to be hottest at that point. And as we expand out, over here on the edge, we're probably going to not have that same intensity. So we could find some average temperature over a region, or specifically the average temperature from some fixed point or some point where maybe the heat source is to maybe P. So that average temperature across that distance. All right, so let's look at a basic example where we find the average value for a function. In this problem, we're going to find the average value for this paraboloid z, my multivariable function, equals x squared plus y squared over this square region defined by 0 to 2 for x and 0 to 2 for y. Well, in order to deal with this, we need our rectangular region. Of course, we know the shape, but we need the area. Obviously, we can find that area using algebra, but let's find the area using calculus since we're in Calc 3. So setting that up using the area formula with double integrals from the previous video, we would say 0 to 2 dA, and we could define this either way, dx, dy, or dy dx. It didn't matter since these were both the same x and y bounds. So finding that area, integrating this, I have x. I'll still have in the front my integral from 0 to 2. I have x. We need to evaluate that from 2 to 0, and then we'll deal with our integral for dy. So that's going to give me 2, 0 to 2 of 2 dy, which is 2y, 2 to 0. And plugging in 2, we've got 4 minus 0. The area of this square region that's too wide and too tall is 4. So we have that area formula here. So now we're going to integrate. We're going to take this function. This is my multivariable function, my function of x and y. We're going to integrate it across those same bounds twice, but we're going to have in front of that 1/4. So in a sense, you could think of this square having those 4 square sub-regions, right? And if we're finding an average, we divide by the quantity of squares So we're dividing by 4 because there would be 4 squares making up that square region. So setting this up, the average value of f across that region R is going to be 1 over the area. And then we have the double integral 0 to 2. 0 to 2, my function z is equal to x squared plus y squared. Of course, you can say dy dx or dx dy. It doesn't matter as the bounds are the same. It means the same either way. Again, conventionally, we normally go z, y, x. So we would do y first and then x. So integrating this function with respect to y, that means x squared is a constant. I have 1/4 the integral from 0 to 2. I have x squared y plus y cubed over 3. I'd rather write plus 1/3 y cubed. And then we're going to evaluate that from y equals 2 to y equals 0. And this is a good example of why I wrote what my bounds are in terms of, because I have 2 variables to plug in here, and we don't want to make that mistake and plug this 2 in for x. All right, so we're eliminating these y's. And I have 1/4. My bounds in x are 0 to 2. This gives me x squared times 2. 2 cubed is 8, so plus 8/3 minus x squared times 0 plus 1/3 times 0 cubed. And of course, that zeroes out. So I have 1/4 the integral from 0 to 2 of 2x squared plus 8/3. Now, these terms are easy to integrate using the power rule. So I have 2/3 x cubed plus 8/3 x from 2 to 0. Obviously, when I plug in 0, those are going to zero out. So I just need to evaluate this at 2, which gives me, I still have this 1/4 out in front. I have 2/3. 2 cubed is 8. Plus 8/3 times 2. I have 1/4. That is 16/3 plus 16/3, or 32/3. 4 goes into 32 8 times. The average value for this integral or this function integrated over the region is going to be 8/3. And so this 8/3 represents that average height. If we think about all of the points in my region from 0 to 2, 0 to 2, I have this average height here. So thinking about that, this represented the volume divided by the area. That's giving me a height. It's giving me one dimension. So the average height from all those points up to my surface of that paraboloid, x squared plus y squared, is 8/3. I hope that helps. Good luck. Email with questions. Don't forget to like and subscribe.